able to do things that are battery powered becomes quite an issue for the user equipment. However, it has to talk to base station or infrastructure equipment. And so in some of the talks here, we'll be focusing on infrastructure. As we look at infrastructure, then we're beginning to think about systems that have more capabilities, that maybe have greater power consumption issues, but also we would like to get to an environment where we don't have to rip out and change all of our base stations every generation. We like to be able to have something that we can continue to use and upgrade within a reasonable time frame. So we'll talk a little bit about FPGAs, the field programmable gate arrays, which are very popular, system on chip type devices. ARM, for instance, is one of the big vendors of system on chip devices, and then GPUs. NVIDIA is really, along with AMD, pushing GPUs to be not just graphics devices, but general purpose computing accelerators. So these configuration challenges then mean that we want to kind of come up with some way that we can reconfigure and not have to have so many different standards. Is this possible? Well, I don't know. But that's, I think, one of the goals and one of the challenges that everyone's trying to sort of address, find ways to be able to have a system that can reconfigure to a bunch of different protocols in a clean way. So as we look at these challenges, one of the things we want to kind of look at are what are the bottlenecks and what are some of the and computation issues. So if we go back and look a little bit at where we've gone, where we're going to, where we've come from, if you go back not that far long ago, 10 years ago, we were still in the 2G, 3G kind of world. Seems kind of quaint right now, but the 2G, 3G world was quite fractured, and the third generation partnership project, which was a way to get some of the American, European, Asian standards to try to begin to interoperate a bit, became kind of important. Now, in this chart, what I'm trying to show is downlink and uplink in terms of the number of antenna type systems, and also trying to look at the time and also the data rate that one might have in a particular cell. So if you go back to the 2G kind of world, 3G kind of world, we're in the 10 megabits per second era with a single antenna typically on a user device and a single antenna essentially sectored, but a single antenna essentially on the base station, what people will call a CICCE kind of environment. As we got into long-term evolution and long-term evolution advanced, LTE, we began to get into environments that went from the single CICCE into what we call MIMO, or multiple antenna communication systems. The acronym MIMO actually comes back from control theory, but that actually is sort of where we're at these days. And so small scale MIMO, 4x4, maybe 8x8, has been around for a while, and it's actually popularized mostly in things like your Wi-Fi devices. So Wi-Fi has sprouted multiple antennas, your laptop hides a bunch of antennas, and so you're able to get reasonable throughput into the gigabit per second range as we're going into those types of environments. Now, 5G is something that we're all kind of working on, and everyone has promised what 5G will be. And if you keep on looking at some of the literature, you'll see that people are talking about 6G, even though 5G isn't really finished yet. But you need to have something to look forward to, so there's always N plus 1G. So really the goals are to be able to try to provide greater spectrum efficiency, and one of the ways of doing that is also by adding more antennas. More antennas allow us to do things like beamforming and direction of arrival kinds of estimation, which actually, if you go back into the 70s and 80s, were techniques that came from radar systems. Now, one of the other concerns is computation requirements. I focus mostly on the physical layer, what we call the baseband, essentially the digital processing that's way down below. So if we assume that we might have a modest 375 megabits per second per user environment in a 100 megahertz bandwidth LTE type scheme, then if we look at how we might want to study this, one of the metrics is number of multiplications per second. And those multiplications per second keep growing. So what I have here in this chart is multiplications on the y-axis, and then the x-axis has this B over U ratio. And what that actually says is number of base station antennas per user. So Tom Marzetta, when he was at I guess it was Lucent at the time, began to look at the study of massive MIMO, and for the last maybe 5 to 10 years, that's become an area of intense research in the academic community, and industry is now beginning to consider this in some of the 5G offerings. So this B over U, or a ratio of usually 4 to 1 or higher, is where we're able to actually get the benefits of having these large antenna arrays to be able to separate users, to be able to beamform, and by doing beamforming, we can have energy go into multiple users at the same time, reduce interference. But this means that to do this, and to support, let's say, 16 users, that becomes then 6 gigabits per second in that cell that gets into the greater than 10 teraflops world, which for a base station is feasible, but still requires a lot of care and design. If you want to have a microcell or picocell, then you're going to be really hardware constrained to be able to do that. In a macro cell, one that handles maybe a kilometer or two, then you have more resources. But these are some of the trade-offs in trying to do the cell planning. Now, what kinds of tools do we have? Well, we started out looking at things that were really single-core CPUs. If you go back to the 4004 from Intel a number of years ago, then that was a single-core device. And through much of the 80s and 90s, as Moore's law allowed us to do greater and greater density of chips and greater clock speeds, we actually did quite well with single-core CPU. However, there were limits in terms of being able to get above that 3-4 gigahertz kind of clock frequency. So the last 10 years or so have been sort of an area where we have multi-core CPUs. And multi-core is great. You'll find 16, maybe greater than that number of Intel cores in some of the latest offerings. However, we're sort of kind of strangled by Amdahl's law, the sequential bottleneck problem. And also the power limitations. You have to be very, very careful about looking at thermal budgets as we go to more and more devices. So one area that a lot of research is going into is what people call heterogeneous computing. So that's something where you combine accelerators, maybe in an ASIC or an FPGA, with the multi-core CPU, maybe with the GPU. So each portion does what it's best at. You may want to do something that's very matrix-based in the GPU, maybe something that's just a simple digital filter type device in the custom ASIC, and then the CPU for the control plane. So that kind of gives us a sense of some of the types of hardware and tools that might be out there. I want to kind of go through maybe 1 or 2 possible scenarios that might be of interest. So when we look at IoT, there's a lot of concern about limited spectrum. Again, there's a lot of spectrum out there, and a lot of it's locked down in various ways. But what people are trying to propose is to use spectrum agility, meaning that I kind of listen to what's out there, I borrow someone else's spectrum, I change frequencies, I change channels, I get out of the way when the primary user comes back into play. So as a sort of an example scenario, just to kind of think about, we've talked a little bit about smart cars and some of those aspects, let's say, of traffic surveillance. So this is from a proposal I put together with some folks in Finland a couple of years ago. We were looking at this issue of traffic surveillance and how we combine things like narrowband IoT with some of the other Wi-Fi and some of the other types of standards that might be out there. And so one of the issues becomes, how do I connect and collect all this data and send it out maybe to a cloud server? So there's this idea of having to have some sort of relay node, and that relay node may support multiple radios, and you may be able to swap back and forth from one essentially standard to another as a certain spectrum opens up, and then you get out of the way when that spectrum is in use again. This requires that agility to be able to swap And also it requires the need to be able to have buffering that might occur. Buffering is not nice, but sometimes you need to have some buffering and also data compression. And that's again where a lot of the interest these days in machine learning and AI come into play. Can we do something in these relay nodes that may be able to help reduce the amount of communication that actually has to go out through the network up to the cloud? So that would mean, let's say in this traffic surveillance example, that we had traffic coming from a high data rate and from a low data rate. We try to combine them in some relay. We try to do some feature extraction. We try to do some maybe license plate recognition in some sort of semi-capable device, and then only the stuff that may be important goes out over some sort of IoT, narrowband IoT, cellular type environment up to some sort of cloud. So we have to be able to swap and adjust and make these types of changes. So I hope that this kind of intro gives you a sense of some of the challenges of IoT, the challenges of communication, and now I want to talk a little bit about area, time, and power complexity. So when we look at area, time, and power complexity, we have another set of trade-offs. And these are sort of efficiency trade-offs. So on the one axis, we have programmability, and on the other axis, we have this issue of efficiency. So I got my start doing ASIC design and doing low-level VLSI design. I still love it. I was teaching that yesterday. I took a flight out this morning to get here because I didn't want to miss my Thursday afternoon class. So ASIC design is great, but it's very time-consuming. And as fab costs keep going up, you may not always be able to do that ASIC. And also, the lifetime of many of our products, as the last keynote from Telus just mentioned, is only a couple years. So unless you're making millions and millions of these devices, you may want to go something that's programmable. So that's where FPGAs from Xilinx and Altera Intel come into play. You lose a little bit of efficiency, maybe a factor of 2, 3, 4, who knows, but you gain the programmability that I can reuse the device. So a lot of test beds these days in the wireless area are built around FPGAs because you can more quickly change the personality of the device to achieve different types of wireless standards and to actually do a lot of experimentation. Now, having said that, if you've done any FPGA programming, if you are a whiz at coding in Verilog or VHDL, you realize that that's not so much fun, and that the rapid turnaround may not be so quick. Even with things like high-level synthesis, Cavallo HLS, Catapult C, all these kinds of tools, it's still a bit of an issue. So that's where GPUs have actually come into the next phase, because things like CUDA, which I'll talk about later, Compute Unified Device Architecture, NVIDIA's tool set, kind of builds on some of the parallel programming tools that people have been using for a couple of years. And so you can write things in C, you can add pragmas, you can do things more in software much more quickly. And so GPUs are really emerging as being kind of a poor man's supercomputer and something where you can buy one for $1,000 that has enormous amounts of power. Of course, CPUs are still there, but they tend to rely more on the control plane, the if-then-else, the state machines tend to be where you use your CPUs. Those are programming. So with that, let's look at a few different architectures and some of the design issues. I'll talk a little bit about high-level synthesis because that is really an interesting area right now, and also talk about some of these different tool sets. So in terms of architectures, there's a huge variety of things these days. GPUs go from things that are Tegra, which are essentially that small form factor tablet device or something that might be in a smart car, way up to server class Titan devices with the newest architecture that have high-speed interconnection networks. The FPGAs keep on increasing in terms of the number of gates that they can have, and some of the newest FPGAs combine ARM cores for programmability and also provide high-speed analog and digital analog converters, the RF SoC that Xilinx introduced about a year ago. Then Multicore, beyond just the plain Xeon device, there's the Intel Xeon Phi, which is essentially 60 or so Intel cores inside one kind of system. Now with all of this, the tool support becomes quite complex. And this is, I guess, where being able to have good software environments kind of collides with having great hardware. So OpenCL, OpenMP, CUDA, SeedHLS, Xilinx System Generator, Bravado HLS, LabVIEW, heterogeneous system architecture concepts. All of these things come into play to try to build up these systems. And many of you have probably used these in some of your coursework or some of your projects or some of your products. So one example methodology would be this one, where we might look at something that we want to put onto mobile SoC. This could be something like a Snapdragon device from Qualcomm, or it could be something like a maybe a Tegra processor from NVIDIA. And this is an example based upon communications and also image processing that one of my students worked on a couple years ago. So we have some wireless communication workloads, we have some computer vision workloads, and other workloads. So you go through this process of trying to do some sort of benchmarking of these workloads, analyze the algorithm, see what's in there, how parallel, what is the memory access pattern, because you waste a lot of time just moving data around. When we start going to, let's say, massive MIMO, and we have 100 antennas, each sampling maybe 100 megasamples per second, we have a huge amount of data just floating around our system. Then there's, of course, the arithmetic complexity. Can I do it in 8 bits? Do I need 16? Do I need floating point? All of these things become important questions that we need to look at. And then in addition to the access pattern, the bandwidth that we have to deal with in terms of the memory, because many of these systems, the read and write over something like a PCI Express bus can be almost too slow. We map that algorithm to the architecture, and we have to decide where we put it. We put it in custom logic, maybe in an FPGA or a Xilinx Zinc chip. We put it in a GPU. If we have a NVIDIA Tegra device, we put it in a CPU. These trade-offs affect the overall performance, not just in where you're placing it, but in how the different modules interact. In my fall course, we do a lot with the Zinc chip from Xilinx, and we use the ICCE bus to move data back and forth. And the students do an accelerator where they build a QR decomposition coprocessor to do a linear system solver. And when they do that, they're often puzzled that their QR decomposition solver creates a slowdown and not a speed up. And that's because the bus interaction sometimes can actually slow you down. Now CUDA, if you've looked at CUDA, it is actually a very interesting environment because it's based upon the idea of multiple threads. So multi-threaded execution is kind of where a lot of these parallel systems are going. And the CUDA environment actually builds on some of the concepts that really came into play with SIMD, single instruction, multiple data computing systems 10, 15 years ago, where you have some sort of host device, and then that host device then talks to a number of different parallel cores that are executing essentially the same program but on different data and then moving stuff back and forth. So that's sort of the abstraction model. And then if we look at sort of the hardware model, we'll see that we have different types of memories. And so data placement in memory then becomes an important aspect of how we get the best performance out of these systems. Now, we kind of built a couple of systems ourselves that used a Xeon host with then a number of GPU boards. So one system had 4 of the GPU boards from NVIDIA, and in this case we were trying to look at how do we best partition the software, how do we handle the memory transfer, and also how do we handle the threads from the main CPU to the different GPU boards using OpenMP through a switch. And so there's a lot of complexity in doing all of this. Now, it's not all GPU. We've also been looking at a number of other parallel test beds. And we had access to a Xeon Phi cluster at one of the supercomputer centers, the Texas Advanced Computing Center in Austin. There they had a number of different clusters that were actually multi-core clusters. And we were able to take advantage of those to be able to take a lot of these baseband algorithms and accelerate them over multiple cores. Doing this, though, requires a good interconnection network, and that becomes one of the challenges. This one was connected with an omnipath network, giving us 100 gigabits per second, which doesn't sound like you would need it, but when you start dealing with things like massive MIMO, you may use it. Now, on a smaller scale, you're actually able to do things also as one of the case studies with some software-defined radio boards. So those of you that played with software-defined radio may have looked at the USRPs from Edis Research, now part of National Instruments, or maybe you've dealt with something called WARP, Wireless Open Access Research Platform, which is an SDR that was developed at my university, at Rice University, and commercialized by Magna Communications. This allows you to do some of the baseband processing in a CPU, and then use an attached radio card to actually do over-the-air tests. So we did this to do an OFDM over-the-air environment, and why is over-the-air so important? Well, in wireless communications, the channel is really what kills you. The wireless channel, compared to a wireline channel, can have a lot of multipath components, and can also have a lot of other attenuation issues. So it's very important to understand what other impairments the uplink radio system and the downlink radio system add to your system. So that's something that we'll get back to as we go through this talk. Another thing we looked at was what's called pre-distortion. You don't think about this so much, but in wireless communication systems, we've been trying to digitize as much of it as possible, but really the last step is an analog power amplifier. And the analog power amplifier gives us the range of communication that we would like to have. So Bluetooth gives us maybe 30 meters, cellular maybe gives you Wi-Fi gives you 100 meters, and then cellular maybe 2 kilometers. But that means we have to operate in a good range for that power amplifier. If we push the power amplifier too far, it distorts. But also it's most efficient just about the point where it begins to distort. So people have looked at a number of so-called pre-distortion algorithms that essentially are digital filters that learn the characteristics of the amplifier and sort of impose an inversion filter so that what comes out of the power amplifier at the highest possible power is not distorted. This has to happen in real time, and we used a CPU with a mobile GPU to actually implement these digital pre-distortion algorithms. So now, what this is trying to say is that we need CPUs, we need GPUs, we need FPGAs, and that kind of is what you're seeing now in user equipment devices, let's say like the Snapdragon family from Qualcomm. It provides the capabilities of having sensors, things like accelerometers, things like temperature sensors, and also sensors like your microphone, and also having other accelerators that are needed. Now, the newest versions of these types of chips also provide some support for neural processing engines. So that's the newest type of accelerator we see in Exynos from Samsung, also from Apple in their I-series chips for their iPhones, in addition to the camera, image processing, the multi-core GPU and CPU. So all these things come together, and if you look at a modern smartphone, the radio is actually almost like a secondary thing, right? We used to have phones that were phones. Now we have a computer that also has radio in it. We'll talk about a few algorithms now in the time that I have left, and just to kind of highlight where we're going with things in 5G, and also give you a sense of the complexity and some of the challenges in trying to build these newer algorithms. So first we'll talk about massive MIMO. It's a big buzzword right now, and everyone likes to try to push something forward. If you build it, they will come type of thing. And so massive MIMO is one of the sort of interesting technologies that's being proposed. Another thing I want to talk about is channel coding. Channel coding, particularly low density parity check codes, are a very big parallel algorithm using everything from the solid state drives to the data packet layer for a lot of our Wi-Fi and in the 5G cellular, and then come back again and talk about the digital predistortion in the case of the power amplifiers, because that becomes important in something called carrier aggregation, which is an area that's being used to deal with chunks of spectrum that are discontinuous. So massive MIMO. Massive MIMO basically says that one antenna on a base station is not good enough, and it's not good enough because we want to have hundreds of antennas that have cheaper, lower quality receiver chains, much the way that the military uses phased array radar. Essentially, is that kind of a concept. We'll have hundreds of antennas. Those antennas then will be in some sort of 2D array, and that 2D array will allow us to be able to sweep and see what's happening. So with massive MIMO, I can beam steer, and I can talk simultaneously with that part of the room and that part of the room, and reduce interference in the middle of the room. And that means I'm sending energy to those people and these people, but not wasting energy on the people who are in the middle. So that's kind of the concept. And then conversely, in the uplink, when those people are talking to me, I don't have to actually spend much time listening to what's happening in the middle. So these are ways to deal with the complexity of being able to support more and more users. Now also this means, this is a little different than small-scale MIMO, like you might have in Wi-Fi right now. Small-scale MIMO does spatial multiplexing. It has multiple streams. Many of our newest Wi-Fi routers simultaneously talk over 2.4 and 5, where they talk at multiple channels in 5. This is more kind of single channels, not trying to get the highest throughput, but it's trying to get better interference suppression to support more users. So there are a number of things that we can do. It's called pre-coding in the downlink, and it's called multi-user detection in the uplink. And many of these things turn out as being linear detectors. Those are the types of detectors that people like to work with, because they set up nice problems, nice matrix problems. So much of the arithmetic signal processing in cellular environments is essentially good old linear algebra. So we'll talk about minimum mean square error detectors, zero forcing detectors, maximum ratio combining detectors, and those are the types of detectors people use in the uplink, similar things for the downlink. Now, there's a challenge of doing this in a centralized processor. If I have all of these antennas listening and feeding all this data into one processor, then that could cause a lot of bottleneck issues. If each of those A to D converters and each of those RF chains is sampling at 100 megasamples per second, I have 100 of them, I have a huge amount of data coming in, which will saturate any kind of bus that I may want to have. And so one of the research interests that my group has had, along with a colleague at Cornell, is to say, what happens if we break this control unit into a bunch of clusters? Now, this idea of breaking things into clusters is not new, but it allows us to kind of work with a smaller system and then be able to reduce the I/O issues in that red bar in the front. Now, if you've done any kind of matrix analysis and you've partitioned a big matrix into sub-matrices and try to work with those sub-matrices, you know it's not for free. So you give up some performance by breaking things into sub-matrices, and you lose a little bit in terms of your capabilities at the expense of a simpler system to actually instrument and build. So now each base station may have local antennas, but those antennas talk to a different cluster, and each of those clusters then talk to each other, and there's a fusion center. That's what this F is here in the middle. This fusion center, which is not showing up today, that fusion center then allows the different clusters to talk to each other. And so essentially we're partitioning a big matrix into sub-matrices. And then we would use some sort of conjugate gradient type scheme to invert a matrix and to be able essentially to find the data that each of the sub-users has sent. So I won't go through the details of the math, but essentially we have something like this where we're going to compare this distributed algorithm and compare it with some other algorithms. The red line that's a little bit hidden there is the centralized mean squared error detector. And then the different blue lines are different iterations of this detector, which we've broken into different sub-detectors in different clusters. Now you notice that if we just have one iteration, we're not exchanging enough data, and so we have actually as bad a performance as maybe an aspect ratio combining detector B. Because we do more iterations and send less data than the full raw samples, we're able to approach the centralized performance. So we do similar things in the downlink, and this is the beamforming problem. And when we do things in the downlink, we also use different timers. Those beamformers use the channel matrices that we estimated in the uplink, and so we use reciprocity, which is a common thing to do in a time division TDD kind of scheme. There's a lot of interest in looking at FDD type schemes, where then you'd have to have a different channel estimation for the up and down, but we're trying to look at things that are time division, at least in this early work in massive MIMO. So this decentralized downlink proceeds in the same way. We have different clusters feeding different antennas, and then we have some consensus step in the middle to try to make sure that different portions of the cluster work together. Now, there are other approaches to this. There's a lot of interest in Europe in something called COMP, coordinated multipoint. There's also another interest in something called cell-free MIMO, where essentially instead of these all being still in one base station, you separate them and have them different antenna heads talk down to a particular user. There's some synchronization issues among those different antenna heads in the base station. And so Cloud RAN or Cloud Radio Access Network is another direction. Samsung has demonstrated some early versions of this in Korea as ways to be able to provide greater coverage and utilize centralized computing facilities. Now, in our work, we looked at these algorithms mapped onto multiple FPGA systems. We looked mostly at the baseband processing. So through Xilinx, we had access to an Amazon Web Services FPGA environment, where there were a number of CPUs connected over PCI Express to FPGA cards. And we did some experiments with this. Those were just purely FPGA cards. There's a newer RF SoC that exists, but that hasn't been actually put into a system chassis that would be able to have that kind of interconnection that we would need. We've also mapped this onto a GPU cluster, a couple of different versions. This initial work was done at a Navy supercomputer through a colleague at the University of Maryland, and there was actually a Cray system that had a number of NVIDIA, at that time, K40 processors. We've continued to work with NVIDIA to look at how this performs on some of their newer devices, and we've been doing some experiments with them with one of their systems in Santa Clara that allows us to look at the NVLink, which is the highest speed interconnect that exists now among 8 or 16 GPU boards. So that's one of the workloads, one of the algorithmic workloads. The other workload I'm going to talk about is LDPC codes. I'll go through this kind of fast, but what I want to give a sense here is why coding is important. Well, when you go through wireless channels, even wireline channels, bits can get upset. If you're doing video, images, it may not matter so much, but if you're doing something that is a really accurate data transmission, FTP of a file, then you may want to make sure that bit flips get corrected. So LDPC is a very parallel environment, and if you go back in 2G, you had convolutional codes with turbo decoders. 3G into 4G, you had turbo codes, which essentially were multiple convolutional codes with an interleaver, and then LDPC provides also interleaving capability. Interleaving is an interesting aspect. If you've looked at wireless channels, there tend to be various dropouts that occur. And so if you send data in a sort of scrambled manner, not as it was sent over time, but interleave it, sort of mix it up, then you're able to recover that back better when you do the decoding. So the decoder fits at the end of the detector, essentially the massive MIMO detector I talked about, and the decoder can be used in everything from WiMAX, Wi-Fi, 5G, to 10 gig and higher Ethernet. Satellite, DBS2, and also SSDs use LDPC for error correction. It's a nice matrix-based algorithm, and it goes back to Cavallo's work at MIT in the 60s, where you essentially have a parity check matrix. You've probably all dealt with parity with memory systems, but this is a low-density parity check matrix, meaning there are lots of zeros in the check matrix. And so basically you create a generator matrix so that when you apply that in a code word, you have a coded transmission that you send that may be twice or less than twice the amount of bits. So rate 1/2 code or twice the amount of data is strong code, but there are codes called 5, 6, 7, 8 that are weaker codes that actually come into play. So you have an iterative process between variable nodes and check nodes, and that goes back and forth, which means that we can set up this Tanner graph and have parallel environment where we have these variable nodes and check nodes that go back and forth, and then we have a final hard decision. So in this algorithm, we map it to a GPU because the GPU is very parallel and it can do a number of computations at once. And so in doing this, we looked at a CUDA implementation where we broke this into multiple kernels. So that's one of the things with GPUs. You break things into kernels, and these kernels do a small task. That task completes the next task, the next task, iterate. So we have an initialization phase where we then go through the decoding iterations, 3 kernels, and then we have an early termination possibly if there are no bits of error, and then we complete the calculation. So this basically means that we have essentially 81 threads in each thread block, and we have up to, in this example case, 172 threads that are sort of happening sort of in parallel. So this matrix is very sparse, it gets spread out. We do the first horizontal processing, then we do the a posteriori probability, APP, value updating, and then we go through a early termination check. That basically says, are all my parity equations satisfied? And if they are, then I skip out and I'm done. Now that sounds great, except that the parallelism in this case may be on the order of working on 2,000-bit code words, but those 2,000-bit code words don't fully occupy, well, they sort of occupy one GPU, but if I want to have even higher and higher throughput, then I can do multi-code word decoding. And what this means is I can pack multiple code words together, and this gives more work for the GPU to do. So in this case, I have streaming into the memory of the GPU, essentially pipelining multiple code words, and so I can now actually be able to get things closer to gigabit performance in a parallel environment with a programmable device. Okay, now our third workload that I'm going to talk about is this issue of carrier aggregation. This started coming up towards the end of 4G, but it's something that people are looking at in 5G. What this basically says is that when you have different bands that are assigned to, let's say, different operators, and different channels that are sort of assigned, then you might want to be able to send more peak data by using more of these carriers at once. But those carriers may not all be in one spot together. They may be separated. They may be in different frequency bands. So we're not going to worry so much what the baseband processing has to do. We have to worry what the power amplifier has to do. So what happens here is by having things that are separated, you begin to get intermodulation distortions that occur between these different carriers that are going out. So if we look at this, and we look at just 2 carriers, which are essentially the 2 blue bars we're trying to broadcast, then because the power amplifier is not linear, we start getting third order and fifth order nonlinearities. So these nonlinearities then create spurs or spurious emissions, and those spurious emissions could end up being in someone else's, some other carrier's channel. So you start interfering with someone else, what people call spectrum mask. You're sort of restricted to broadcasting a certain range. If you have junk coming out outside of that range, then you're doing something that is improper. You also want to bring this down maybe 50, 80, 90 decibels below what you actually can send. So this becomes a real-time signal processing problem, and it also becomes a problem where we have to go through some sort of training phase. So if we want to look at something like a block diagram of the system, what we did is we did a MATLAB block diagram that essentially went through and did some of the training, and then we used an SDR board, in this case one of the Warp radio boards, and in that radio board we characterized the power amplifier by feeding back some of the signal that was transmitted to a receiver port. And then we did a down conversion, and we looked at the signal that was sent. We looked at it to see how distorted it was, and then we used a LMS type, least mean squared algorithm, to be able to do some sort of pre-distortion and mix in that signal, so what went out now was actually a distorted signal going into the power amplifier, but what got broadcast looked good. Now this scheme is not just used in digital pre-distortion. There's similar things that are used in full duplex communication. Full duplex is another scheme that people are looking at as a way to increase the spectral efficiency. In most of our communication systems, you have a broadcast, transmit phase, and a receive phase. And that's because whatever you broadcast kind of leaks back and can affect your receiver. So in full duplex communication, you try to broadcast while you're actually receiving, and you do some sort of cancellation of what you're sending out. We do a very good job in being able to echo cancel, if you will, as you speak. You sort of hear what you're saying, but you hear what other people are saying too. It takes a little bit more to be able to train a communication system to be able to talk and listen at the same time. So this kind of pre-distortion is a way to be able to speak louder and not speak inaccurately. So this digital pre-distortion now becomes sort of a challenge to be able to do in real time. And so one of the things that we wanted to use was this hardware platform called Warp. And this was developed over the last 10 or so years at Rice. This is the third generation, which now is getting a bit old, based upon a Vertex 6 FPGA. We put everything into the FPGA in terms of the baseband processing, and we used a microblaze or soft core to be able to do some of the packet processing, and we had Ethernet connection to be able to send data out. So this idea of being able to build a software-defined radio platform, whether it would be Edis Research's USRP or Warp, allows you to be able to do interesting over-the-air tests, things that you can connect to a spectrum analyzer and actually look at what's being sent. You can also be able to look at some of the distortions and understand the SNR and the SINR issues that come into play. Now with Warp, we had two modes, a mode where everything happened real-time in baseband in the FPGA, and then a prototyping mode where we used MATLAB to be able to pre-process the data and post-process the data. So with this kind of an environment, we can do over-the-air experiments. And so we can actually model and use a real power amplifier, and with that, we can also understand some of the distortions that occur and how we're able to reduce some of the out-of-band signal that we were sending. Now this idea of being able to do things with power amplifiers, to be able to do things with some sort of design environment led to also an environment at Chalmers in Sweden. They have, through some collaboration with Ericsson, something they call RF Web Lab, and they have a Cree power amplifier that we also used to be able to tune our algorithms for that amplifier as well. Because each amplifier has different characteristics, and as you kind of change those amplifiers, we have different spurs we have to be able to suppress. Now, as we go from 2 to 3 subcarriers, we have even more complexity. A lot of narrowband IoT may actually be using a very small carrier that's in the middle of something else that you care about. So narrowband IoT, which is one of the schemes that people are proposing for instrumentation, again, long-range, low-power instrumentation, may be in the kilohertz range, maybe a kind of a weak signal, but slotted in among other devices and other higher power devices. So what we're trying to do here is see if we have 3 subcarriers, can we suppress and be able to reduce some of the spurious emissions outside of band. So by doing this, we were actually able to reduce some of the spurious emissions, and in this case, we were using a situation with no DPD and then also adding digital print distortion and being able to bring down that additional 3rd spur. It's kind of ugly, as you can see. It only brings it down, in this case, about minus 30 to minus 40 dB. And that minus 40 dB is maybe not good enough, but if you go out farther from those primary carriers, you can see we're down in the minus 50, 60 range. So that was the 3rd environment that I want to talk about. And now, just to kind of close the loop on some of the platforms, again, we used a NVIDIA device with this, and we actually programmed this up and connected to a spectrum analyzer. That was essentially what we saw a few minutes ago in that previous graphic. So now with some discussion of challenges in terms of communication systems, with some discussion of area time complexity and architectures, and some of the 5G algorithms, I want to talk a little bit about test beds. And test beds are sort of an interesting area because they have a number of challenges, both for communications folks, signal processing folks, computer engineers, and then eventually as people want to be able to take these devices and produce systems or products, we have then a number of challenges in trying to convert things. So one of the challenges is trying to look at design space exploration. What should I use? How much should I use? What are the area time power limits that I have? And then if we have this personal cloud idea, then we have to figure out how we can also do some local processing or edge computing when we may be able to utilize some of those resources that are maybe idle when we're not actually communicating. We're not communicating all the time. We may be able to buffer data and do some data compression, kind of in a sensor network sense. Now, the programmable test beds have been involved in a lot of industry research, and also there are a number of companies that have been involved. And I want to sort of talk about one of the test beds that was an extension at Rice called Argos. And this is a test bed that my colleagues have been developing. And Argos is one of the early massive MIMO test beds. In this test bed, we collected a number of the boards I just showed you, which were basically these work boards, and we provide radios in front of them. These were in the 2.45 gigahertz Wi-Fi bands, and we had on the order of roughly about 90 or so, 96 radios that were connected together. When you look at these systems, though, you'll see that the antennas on the front take up a fair bit of space, and that's one of the reasons that people are trying to look at millimeter wave systems as well, in the 28 and 60 gigahertz range. But those systems are usually sort of thought about for more line of sight, while the sub-6 more for broader communication. A lot of cables in the back. Those cables are ugly and create a lot of complexity in synchronization and timing and control. Now, I've been talking about a lot of Rice activities. Of course, other people are doing similar things, and National Instruments has a collaboration with Lund University in Sweden, and they have their system there. And that system at Lund, the top part looks like a T, is actually their antenna array, a custom antenna array of patches. And then below, you'll see the various RF boards, and then below that, a lot of cables go into some of the FPGA environment. Off on the right upper picture is a big station at Bristol in the UK, They've also been using a number of the National Instruments boards, and they've been able to get very high data rate with, I believe, over 100 radios there. At the bottom is Sora, which was a Microsoft research project in China to look at using, again, some general-purpose processors in this context. Now, we can talk a little bit about university-industry partnerships, and the National Science Foundation, whenever they come back from their hiatus, has been working on something called POWER, Platforms of Advanced Wireless Research. It's a consortium with about 30 or so different industries, and also with a number of universities. The first cycle competition was last year, and 2 projects have just started. One project is called Cosmos, and that's a collaboration of Rutgers, Columbia, and New York University Poly. And Cosmos is focusing on millimeter wave, and also in test beds in New York City, trying to look at some of the issues with channel modeling in the caverns among high-rises to be able to show how the scattering that occurs among high-rises will hopefully be able to lead to reasonably good communication systems and not be just blocked totally by all those towers. So this is one of the platforms that was awarded last year. Another platform is one at Rice, and it's called Renew. And this platform builds on the massive MIMO platform Argos, but now uses a new SDR board built around the Xilinx Zinc chip. And that is a partnership with the University of Utah with their powder testbed. And that picture shows essentially a collection of about 8 or 9 radio cards. And these were designed to avoid some of the cabling, so the edge connectors snap together. And then on the right-hand side, the red cable is a single node that would be used for equipment. That can be battery powered, so you can move it around. And then that larger array is one layer in a shelf. And this box on the left is one of the first generation platforms that essentially can go up to about 96 radios. And each shelf there has about 10 radios, and the little circle is the antenna. So this Powder Renew is just getting off the ground. It was awarded in March of this year, and Rice is working with the University of Utah to deliver one of these massive MIMO platforms for experimentation by university and industry folks. And so this is something that we're looking for experiments and proposals for experiments. And talks like this are ways for us to tell the community that these resources are available and that we're trying to make these accessible for experimentation and design. So as I round up, I just wanted to sort of mention a number of the collaborators. Of course, a lot of this work is being done with a number of different folks at Cornell with Christoph Studer, folks at Rice in my group, folks at Finland in Tampere, and in Oulu, and also the University of Maryland on DPD, and then the testbed systems are in partnership with my colleagues at Rice and also the University of Utah, and partners at Xilinx as well. So just to summarize, what I tried to discuss today was essentially a lot of the challenges in communication systems as we go into the 5G era with small devices, Internet of Things, to be able to provide the capability to be able to have these small devices communicate in an urban environment, in a rural environment, in your home environment, and how that affects the architecture issues, the algorithm issues, and how test beds can be very important to be able to allow us to build these systems. Thank you very much.
Wow, like drinking from a fire hose. Thank you. We do have some time for questions. Just check with the chair. Our next session will start at 2 o'clock, which is the future directions. So we do have some time, and there'll be a time for a short break as well. But right now, we've got an opportunity for some questions.
Archie?
So this hardware that we discussed, and it's a very interesting talk that I liked. I have a quick question that is for edge computing point of view, if we want to evaluate how good or it is. what kind of power consumption and what kind of latency we are talking about for the hardware device? What is the power consumption?
Oh, power consumption. Yes. So this work has been mostly algorithmic based, and so we've been kind of looking at power consumption issues for the user equipment, and so that would be more FPGA at this point. That is not going to be essentially what would happen in a finalized product, but for a prototype, the FPGA can run off of a battery for several hours, providing the radio communication as well. For the infrastructure side, then we're trying to look at GPUs, and GPUs themselves are 100-watt type devices. So if we aggregate when we were maybe 480, then we do have a very large power budget for that system. The idea that eventually could maybe be hardened into FPGAs, which would bring down the order of magnitude and then potentially into ASICs. But when people are trying to do something refined radio, even for the base station, we're trying to see what we can do. A number of startup companies, Matthew in Dallas, that's using a number of these types of tools to be able to try to build semi-commercial systems. It's the configurability we're trying to get to. So yes, power is to be an issue, and it's something we're trying to instrument to watch, but yes, it definitely is.
One last question here.
Okay, I am Himanshu Thapia from Institute of Kentucky. My question is that, for example, especially in the 5G domain, what do you think that, especially from the power perspective, how much RF power can play a role to charge the IoT nodes or other types of devices like that?
You're talking about energy harvesting? Or
Yes, energy harvesting.
Energy harvesting is an interesting question. There's been some work done on that in terms of taking RF from Wi-Fi and using that to power various devices. With the massive MIMO, that's actually kind of contradicting what you're talking about. What the massive MIMO is trying to do is not waste energy by sending it everywhere, but just send it more focused to you. So if I'm sending it just to you, you're going to get recharged, but this category is not. That's, I think, an interesting question. It's not something that people have really considered in terms of the overall ecosystem. Right now, the focus has been, instead of having high power amplifiers blasting energy everywhere, reduce the power by having smaller, potentially more efficient devices targeting multiple users. But that's definitely a really important question if we want to try to do energy harvesting.
Small token of messages for the keynote speaker.
Keep going. Okay. Thank you. Thank you very much. Thank you.
Take a minute or two for a break, but we're going to try and move really quickly into the future directions thing. I'll make a couple program note announcements. There is an error in the hard copy. The networking lunch is tomorrow, not today. Big deal, right? You'll be here for lunch. If you haven't picked up a hard copy, please pick one up at the front desk. And as you're on your way out, could you pick up the trash and either put it in one of the receptacles over here, or receptacle over there, and if it doesn't fit, just pile it up around the table in the back there. So we'll clean things up.